Hello, my name is Samantha. I am in Team 4 alongside Caitlin, Alessandro, and Madeline. We did our project on light and sound pollution. So our project goal was mapping the correlation between light and sound pollution in several urban areas. So noise pollution is a result of industrial activities, commuting air travel that contributes to the overall loudness of ambient noise in an area. Light pollution has several variants. We cared about sky glow in particular as a quantifier of pollution, which was defined as scattered light in urban areas resulting in a glow. Illuminance is the flux of light intensity. Its SI units are lux. What we expected was that urban areas with denser populations would have more pollution. Health consequences as a result of light and noise pollution ranges from increased irritability to even cardiovascular issues. We had two desirable sensors, microphone and light sensors. So what we expected out of our microphone was that it would have no built-in filters, as well as being sensitive from the 20 hertz to the 20 kilohertz range, which is the frequency range of human hearing. For our light sensor, we wanted high sensitivity and low light levels, so we chose a photodiode. We also looked for through-hole interfaces, a spectral range and visible light spectrum, and thorough documentation for circuit design considerations.
The photodiode we selected generates about 10 nanoamps of current in absolute darkness. The setup portrayed would theoretically over-amplify the signal, but after conducting some experiments with just a transimpedance amplifier, the signal was not strong enough, so we added the non-inverting amplifier to get the signal on the order of hundreds of millivolts. For the microphone, we determined that we would need a gain of about 100 in order to sufficiently amplify the signal to make it well detectable with the 4 millivolt resolution from our Arduino. We used two non-inverting amplifiers, each with a gain of 11, yielding a net gain of 121. Since the microphone outputs AC signal, which goes negative, we needed to offset the signal in order to keep it from getting clipped at 0. In order to do this, we placed the voltage divider before the amplifiers. So we chose our resistors to create a net average output voltage of 2.2 volts, which is pretty close to the center. We decided to make an enclosure in order to protect the components as well as improve the user experience. The enclosure has the microphone adhered to the side of the box to prevent muffling of sound. Additionally, there is a square hole cut out of the top of the box in order to expose the photodiode to the light in the sky.
The first data models we looked at were the well-established levels of light and sound pollution, the maps on the top left and right. Because the maps have a common distribution of bright spots, we hypothesized that we would observe positive correlation between the light and sound levels that we measured. We also noted that maps of population density, like that on the bottom, had the same distribution and thought both metrics would have a positive correlation with that as well. Finally, we used sensor datasheet information to design our circuits. We each took a number of sound and light measurements during the day and night, respectively. For the photodiode data, we didn't have a good way to calibrate the circuit output to standard light units, so we reported our measurements in millivolts. For the microphone data, we first made millivolt to decibel Z calibration curves like that on the top right using an app. The curves were used to convert the magnitude of the Fourier transform of our voltage data, top center, to decibel Z. Then we applied an A weighting curve in the lower left, so the magnitudes reflected the fact that humans perceive some frequencies as louder. Finally, we integrated corresponding intensities and converted back into decibels.
The measured light pollution at each location is consistent with the light pollution model. According to the model, the sky quality meter should be negatively correlated with measured light values. So as expected, the largest sky quality meter value of 19.07 corresponds to the lowest light level of 38.3 millivolts. As for our sound data, the range of human hearing is within 20 to 20,000 hertz. Thus, we expected frequencies within that range to have significant peaks due to ambient yard noises, such as from birds chirping or cars passing. However, we did not expect to find 0.1 millivolt peaks across all frequencies, as you can see on our right FFT, which is from data collected from Tucson, Arizona, which we found was from the random noise when the microphone was removed and shorted, which you could see on the left FFT. Although we did not see a strong correlation between the measured light and sound, we found a positive correlation between population density and sound and light pollution with an R-squared value of around 0.86. The measured value suggests that the light pollution in all locations range from about 38 to 40 millivolts, and the sound ranges from 54 to 57 decibels, which is typical for suburban environments. However, due to our smaller sample sizes that were taken in data collection, we have large error bars on some of our data points. Some future experiments may include verifying the correlation between population density and measured sound and light pollution because our R-squared values aren't as high as we would like, and also exploring areas with little human-made light pollution, such as the desert, and also being able to explore the frequencies in different occupations, such as construction sites.